Right now, in the room where you are lying, a silent rain is falling. It is moving through the roof of your building, through the ceiling, and down into the space you are occupying. It is passing through the blankets, through your skin, through the organs in your chest, and through the floor beneath you, continuing its journey deep into the crust of the earth. It does not slow down when it meets the resistance of your body. It does not collide with the atoms that make up your bones or your blood. It leaves no trace of its passage. Approximately 85% of the matter in the universe is completely invisible. Billions of its particles are passing through your body right now, entirely unimpeded, moving at hundreds of kilometers per second. We know exactly where this substance is. We can map its structures across millions of light years. We can weigh it to a high degree of precision, and we have absolutely no idea what it is. There is one question that runs underneath everything tonight. How did we manage to map and weigh an invisible universe when we still do not know what it is made of? By the end of this, you will understand how humanity learned to look past the light, and how we found the heavy, invisible architecture that holds the cosmos together. Now, let us begin. Everything you have ever seen, touched, or known belongs to a very specific, very rare category of existence. The device you are listening to, the air moving through your lungs, the iron at the core of the Earth, the glowing dust of the Orion Nebula, the surface of the Sun, the black hole at the center of the Milky Way, all of it, combined, makes up roughly 15% of the total matter in the universe. The visible universe is a rounding error. The overwhelming majority of the physical world is made of something else, something that refuses to interact with us. For the entirety of human history, astronomy rested on a single, unchallenged assumption. Light meant mass. When ancient astronomers looked up at the night sky, they mapped the stars, tracking their slow procession across the celestial sphere. When Galileo Galilei ground his own lenses and pointed his telescope at Jupiter in 1610, he was capturing photons of light that had reflected off the planet and its moons. When William Herschel mapped the deep sky in the late 18th century, he was hunting for the faint, glowing smudges of distant nebulae. The logic was simple and entirely reasonable. If a region of space was bright, there was matter there, a star, a planet, a cloud of heated gas. If a region of space was dark, it was empty, or, at the very least, it held a cloud of cold dust obscuring the light behind it. And even cold dust could eventually be seen, if you looked at it with the right instruments. This assumption held firm as the centuries passed, and our tools grew more sophisticated. We learned that visible light is only one narrow sliver of a much wider electromagnetic spectrum. A star does not merely emit the light our eyes can register. It emits radio waves, microwaves, infrared radiation, ultraviolet light, X-rays, and gamma rays. Each of these is the same phenomenon, electromagnetic radiation, simply carrying different amounts of energy. Normal matter, the 15%, is deeply tied to this spectrum. It is loud. It interacts. If you heat a cloud of hydrogen gas, its electrons jump to higher energy states and then fall back, emitting photons at precise wavelengths. If a star exhausts its fuel and explodes, it releases a blinding flash of gamma radiation. If cold dust sits in the void, it absorbs starlight and re-emits it as a faint thermal glow in the infrared. Even black holes, which emit no light of their own, are ringed by accretion disks of superheated matter that blaze across the X-ray spectrum. Normal matter cannot help but announce its presence. It absorbs light, it emits light, it reflects light, it scatters light. Dark matter does none of these things. It opts out of the electromagnetic spectrum entirely. If you shine the most powerful laser ever constructed directly into a dense cloud of dark matter, the light will not scatter, it will not reflect. It will pass straight through as though the space were completely empty. If you point the most sensitive radio telescope ever built at a dark matter halo, you will hear only static. If you search for the thermal signature of dark matter using infrared detectors cooled to near absolute zero, you will find nothing. It does not emit, it does not absorb, it does not reflect, it does not cast a shadow. This is why the name dark matter is fundamentally inadequate. It is not dark the way coal is dark, or the way the bottom of an ocean trench is dark. Coal absorbs light. The ocean scatters it. A more accurate term would be invisible matter or transparent matter. It is a substance that exists outside the rules of electromagnetism altogether. Consider what this actually means for the room you are in. Imagine you could gather a handful of dark matter and try to hold it. There would be nothing to hold. Your fingers would close on empty air, because your fingers interact with the world through the electromagnetic force, and dark matter does not answer to it. You could not feel its temperature, because temperature is carried and exchanged through electromagnetic interactions. You could not see it in any light, warm it with any fire, freeze it, burn it, or trap it in any container, because a container is only a set of walls, and walls only stop things by pushing back electromagnetically. To dark matter, the wall is not there, the floor is not there, the planet is barely there. It responds to only one thing in the entire physical world, the gentle, long-range pull of gravity, and gravity is by far the weakest of the fundamental forces. It takes the entire mass of the Earth to hold you gently to the ground. So a single dark matter particle, feeling only that weakest of forces, drifts through the whole planet, almost as though the planet were a faint suggestion rather than a solid thing. And because it ignores electromagnetism, it also ignores the physical forces that let you touch things. When you place your hand against a wall, the atoms in your hand do not actually make contact with the atoms in the wall. The negatively charged electron shells of your atoms repel the negatively charged electron shells of the wall. The electromagnetic force pushes back. That resistance is the entire sensation. You know as solidity. Dark matter carries no electromagnetic charge. It has no electron shells to push back against ordinary matter. This is why the particles drifting through your room tonight do not stop when they reach the roof. They do not feel the resistance of the concrete or the wood or your skin. To a dark matter particle, the entire Earth is a loose collection of widely spaced atomic nuclei, and the gaps between those nuclei are so vast that it simply drifts through without noticing. For decades, the existence of such a substance seemed absurd. Why would the universe build most of itself out of a material that cannot be seen, touched, or measured by any conventional instrument? The answer lies in the one force that dark matter cannot ignore. It may be blind to light and deaf to electromagnetism, but it feels gravity. It possesses mass, and because it possesses mass, it warps the space and time around it. It pulls on the things we can see. Gravity is the only language dark matter speaks. It is the only translator we have. When astronomers finally grasped the sheer scale of this invisible mass, it quietly rearranged our sense of where we live. We are not inhabiting a universe of galaxies separated by vast empty voids. We are inhabiting a universe almost entirely filled with a massive, invisible ocean of dark matter. The galaxies we see, the swirling spirals of billions of stars, the glowing nebulae, the supermassive black holes are tiny, luminous islands suspended within that ocean. We are the exception. We are the rare, brightly glowing ash scattered across a structure we cannot see. There is a question hiding inside all of this, and it is the one that made dark matter so difficult for so long. If this substance does not speak to light, and it does not touch our atoms, how do you ever catch it? If a thing is both invisible and untouchable, how did anyone prove it was there at all? You prove it by watching a collision. When things crash, they reveal the rules they obey. In the constellation of Carina, roughly 3.7 billion light-years from Earth, there is a structure that astronomers call the Bullet Cluster. It is one of the most important objects in the history of this entire subject, and it is not a single thing. It is a wreckage site. It is the aftermath of two enormous galaxy clusters slamming into one another at a scale of speed and mass that is difficult to hold in the mind. To understand what happened here, you have to understand what a galaxy cluster actually is. A cluster is one of the largest gravitationally bound structures in the universe. It contains hundreds, sometimes thousands of individual galaxies, but the galaxies themselves account for only a small fraction of the ordinary matter in the cluster. Most of the ordinary matter is not locked inside the galaxies at all. It exists as a thin, immense cloud of superheated gas that fills the space between them, a fog of plasma spread across millions of light years. This gas is diffuse, but because the cluster is so vast, the total mass of the gas is staggering. In most clusters, there is far more ordinary matter, in this intergalactic plasma than in all the stars of all the galaxies combined. The gas is heated to millions of degrees, and it glows faintly in the X-ray part of the spectrum. To human eyes, it is invisible, but to an X-ray telescope in orbit, it is one of the brightest features in the sky. Hundreds of millions of years ago, a smaller cluster drifted toward a larger one. They were drawn together by their mutual gravity, accelerating across the void until they were moving at millions of kilometers per hour. And then they collided. This was not a collision of solid objects. Galaxies are mostly empty space, and clusters are emptier still. When two clusters merge, the individual stars almost never strike one another. The galaxies pass through each other like two flocks of birds crossing the same patch of sky, each bird missing every other bird. But the intergalactic gas is different. It is a fluid. And when the massive gas cloud of the smaller cluster met the massive gas cloud of the larger one, at that tremendous speed, it could not simply pass through. Fluids do not do that. The two clouds met and they resisted each other, exactly as two bodies of water resist when they collide. In the year 2006, an international team led by the astronomer Douglas Clow pointed two of humanity's most capable orbital instruments at this collision. They used the Chandra X-ray Observatory to look at the superheated gas, and they used the Hubble Space Telescope, together with several ground-based telescopes, to map the mass. What Chandra saw was a record of extraordinary violence. As the two gas clouds collided, they generated tremendous friction. The smaller cloud drove through the larger one like a projectile. It's a bullet, and the drag of that passage heated the gas even further, up toward 100 million degrees Celsius. Ahead of it, the gas piled up into a massive bow shock, the same shape a supersonic aircraft leaves in the air, frozen here at the scale of a galaxy cluster. The instrument mapped this heat precisely. In the data, the ordinary matter appeared as a bright wedge of superheated plasma, and it had clearly been slowed down. It had crashed. It had behaved exactly the way fluid dynamics says matter should behave when it strikes a wall of other matter. But the team was not only interested in the gas, they wanted to know what had happened to the gravity. They wanted to know where the mass was. To weigh the clusters, they used the light of far more distant galaxies lying billions of light years behind the collision. Because mass warps space, the gravity of the bullet cluster acts as a lens. It bends and distorts the light of those background galaxies as it passes through. By measuring exactly how much that distant light had been stretched and sheared, the team could calculate precisely where the mass in the cluster was concentrated, regardless of whether that mass emitted any light of its own. When they laid the map of the mass over the map of the superheated gas, the two did not line up. The glowing plasma, the ordinary matter, was tangled in the center of the collision, dragged and slowed by friction. But the great majority of the mass, the gravity itself, was nowhere near the gas. It sat far ahead of it, on either side, exactly where the galaxies had ended up. The mass had not slowed down at all. During the collision, the dark matter halos surrounding the two clusters had simply passed through one another. They felt no friction. They did not heat up. They emitted no X-rays. Because dark matter cannot interact electromagnetically, the two invisible clouds had no mechanism to slow each other down. They coasted straight through the wreckage, leaving the ordinary gas behind them, stranded in the middle. When the team assembled the composite image, they color-coded the superheated gas in pink and the gravitational mass in blue. In that image, the blue mass is completely separated from the pink gas. The gravity has come apart from the light. That separation was the smoking gun. For decades, some physicists had argued that the missing mass might just be ordinary matter too dim to detect burnt-out stars, cold planets, clouds of dark dust. But the bullet cluster made that impossible. If the unseen mass were ordinary matter, it would have felt the friction. It would have crashed with the gas and stayed trapped in the center. Instead, the mass moved under a completely different set of rules. It proved that dark matter is a distinct physical substance, one that ignores the forces governing everything we can touch. It is a thing that carries enormous weight and casts no light. A few years later, astronomers found a second colliding cluster with the same signature. It was a smaller, more distant collision, and because it echoed the original so closely, they nicknamed it the baby bullet. There again, the superheated gas sat trapped in the middle while the gravitational mass had sailed on ahead to either side. Then a third example appeared, and a fourth. each one told the same story. The gas slows. The mass coasts through. The bullet cluster is not a fluke. It is a category. Honesty requires one complication here, because the picture is not perfectly clean in every case. There is a cluster collision, an object astronomers nicknamed the train wreck for the sheer disorder of it, in which the mass reconstruction seemed to show a dense concentration of dark matter sitting right on top of the hot gas, where the simple theory says it should not be. For a while this looked like a genuine problem, a case where dark matter behaved exactly the way it is not supposed to. Later, more careful analyses using deeper images disagreed about whether the dark core was really there at all, and the balance of evidence shifted back toward the ordinary picture. This is worth saying plainly, because it is how the field actually works. The evidence for dark matter is not a single perfect image. It is a weight of many observations, most of them pointing the same way, a few of them stubborn and unresolved. The stubborn cases do not vanish. They sit in the literature, waiting for better data, and the honest position is to hold them alongside the rest rather than tidy them away. The bullet cluster remains one of the most direct pieces of evidence we have that the invisible ocean is real. It gave us a visual map of a substance that refuses to be photographed. So we saw it clearly in 2006. We had the orbital telescopes, the supercomputers, and the accumulated physics to read the bent light of distant galaxies and reconstruct the wreckage. But there is an obvious problem with beginning the story there. Nobody points a billion-dollar X-ray observatory at a random patch of sky on a hunch. Somebody had to suspect the invisible ocean existed long before there was any technology capable of seeing it. Somebody had to notice the universe misbehaving decades earlier, with almost nothing to work with. To find that person, we have to go back to 1933, to the California Institute of Technology, and to a man who made a lifelong habit of noticing things that everyone around him preferred to ignore. His name was Fritz Zwicky. He was a Swiss physicist, born in Bulgaria, working in the United States. In the history of astronomy, Zwicky occupies a strange and uncomfortable position. He was undeniably brilliant. He was the first to propose the existence of neutron stars, only a year after the neutron itself was discovered. He predicted that galaxies could act as gravitational lenses decades before anyone observed one. He coined the term supernova, and he correctly proposed that supernovae were the transition of ordinary stars into neutron stars. He had an intuition for the cosmos that seemed to run a full generation ahead of his colleagues. He was also, by almost every account that survives, intensely difficult. He was combative, dismissive of anyone he judged less capable than himself, and fiercely territorial about his ideas. He is remembered, among other things, for calling certain colleagues at the Mount Wilson Observatory spherical bastards. When asked what he meant, he explained that they were bastards whichever way you looked at them. His temperament is not a footnote here. In the story of dark matter, Zwicky's personality is a structural element, because it helps explain how one of the most profound discoveries in the history of physics could sit buried, in plain sight, for 40 years. It is worth pausing on how much this one man saw before anyone else. Working alongside the German astronomer Walter Baade, Zwicky proposed in 1934 that when a massive star exhausts its fuel and collapses, it does not simply fade out. It detonates in a colossal explosion, and its core is crushed into an object of almost unimaginable density. A star made entirely of neutrons, a city-sized sphere heavier than the Sun. This was a single year after the neutron itself had been discovered in a laboratory. The idea that an entire star could be built from them was so far ahead of its time that it was treated, at first, as fantasy. It would be more than 3 decades before a neutron star was actually observed. Zwicky and Baade also gave the exploding stars their name. They called them supernovae, and they proposed that these explosions were the source of the cosmic rays constantly striking the Earth. On every count, over the span of decades, they were shown to be right. Zwicky did not merely theorize. He built a supernova search at the Palomar Observatory and hunted these explosions himself, night after night, comparing photographic plates of the same patches of sky taken weeks apart, looking for a new point of light that had not been there before. Over his career, he found more than 100 of them, more than any single person had ever found. He compiled vast catalogues of galaxies and clusters, tens of thousands of objects, work that later astronomers would mine for generations. He was, by any measure, one of the most productive and original minds of his era, and he spent much of his life on the outside of the community he was transforming, partly because of the difficulty of his manner, and partly because he insisted on looking where others had decided there was nothing to see. The Coma cluster measurement was of a piece with the rest of him. He looked at a swarm of galaxies, did the arithmetic that everyone else could have done, and reported an answer that everyone else preferred not to hear. In the early 1930s, Zwicky turned his attention to the Coma cluster. The Coma cluster is a vast structure, roughly 321 million light-years from Earth, in the constellation of Coma Berenices. It is a great spherical swarm containing over 1,000 identified galaxies. Zwicky wanted to answer a simple question. He wanted to know how much the whole cluster weighed. In astrophysics, you cannot set a galaxy on a scale. You have to infer its mass from its behavior. In 1933, there were essentially two ways to estimate the mass of a distant cluster. The first was the luminosity method. You look at the cluster through a telescope. You measure the total amount of light coming from all its visible galaxies. You know roughly how much light a typical star gives off, and roughly how much mass that star has. So by counting the light, you can estimate the number of stars. And from the number of stars, the total mass of everything that glows. The second method ignored the light and looked only at motion. A cluster is a gravitational tug-of-war. Its galaxies are not sitting still. They swarm around the center at enormous speeds, and all that motion is kinetic energy trying to fling them outward into empty space. The only thing preventing the cluster from evaporating is its own gravity, pulling inward, fighting the outward rush. This balance is described by a principle called the virial theorem. If you can measure how fast the galaxies are moving, the virial theorem tells you exactly how much gravitational mass is required to hold them together. If there is too little mass, the gravity is too weak, and over time the cluster must scatter and disperse. Zwicky decided to use both methods and compare the answers. To measure how fast the galaxies were moving, he used the Doppler effect. When a galaxy moves away from us, the light it emits is stretched toward the red end of the spectrum. When it moves toward us, the light is compressed toward the blue. By passing the light of the Coma galaxies through a spectrograph, an instrument that splits light into its component wavelengths, Zwicky could read these shifts and calculate how fast each galaxy was moving relative to the center of the swarm. He obtained velocities for 8 galaxies within the cluster. The numbers were far larger than he expected. The galaxies were moving at average speeds of roughly 1,000 kilometers per second. At that speed, a galaxy carries an immense amount of kinetic energy. To keep a swarm of them moving that fast from tearing itself apart, the cluster needed a gravitational anchor of enormous weight. Zwicky took the mass required by the virial theorem, and he set it beside the mass he had calculated from the starlight. The two numbers did not match. They were not even in the same neighborhood. By his calculation, the Coma cluster was moving so fast that it required something on the order of 400 times more mass than the visible stars could provide. Even allowing for the crude instruments of the day, even correcting for the errors in the assumed distance to the cluster, and those errors were real, because the cosmic distance scale itself was badly miscalibrated, in 1933 the discrepancy did not go away. It shrank, but it remained catastrophic. If the visible light were the only mass in the Coma cluster, the cluster should not exist. The gravity of the stars was far too weak to hold it. The galaxies should have slipped their gravitational bonds and drifted apart into the intergalactic void billions of years ago, but they had not drifted apart. The cluster was still there, a tightly bound sphere of galaxies holding its shape across deep time. Zwicky drew the only conclusion the mathematics allowed. The visible stars were nearly irrelevant to the structural integrity of the cluster. The vast majority of the mass had to be invisible. It was supplying the gravity, and it was giving off no light. He published this in 1933 in a Swiss physics journal, written in German. In the paper, he stated that if his velocity measurements were correct, the surprising result was that dark matter existed in far greater quantity than luminous matter. He used the German phrase Dunkelmaterie, dark matter. It was a carefully reasoned argument, grounded in measurable mathematics. He had looked into the void, measured the tension in the ropes, and shown that something invisible was holding them taut. and the astronomical community responded with silence. The silence was not a conspiracy. It was a combination of technical limitation and human friction. In 1933, measuring galaxy velocities was brutal, exhausting work. Exposing a single glass photographic plate could take hours in the freezing air of a mountaintop dome, with the astronomer manually guiding the telescope the whole time to keep the target centered. Many astronomers simply did not trust Zwicky's velocity figures. The implication was also deeply unwelcome. To accept Zwicky's conclusion was to accept that the entire discipline of astronomy, the charting of stars, the measurement of light, was only skimming the surface of a universe that was mostly hidden. And then there was Zwicky himself. He was not a man who built consensus. He did not gently invite colleagues to check his arithmetic. He announced that he was right, and treated those who could not see it as fools. And he was not, in the end, a good ambassador for his own idea. So the paper was largely set aside. A few years later, another astronomer named Sinclair Smith measured the Virgo cluster and found the same kind of discrepancy. But that too failed to catch fire. The missing mass in these clusters became a piece of esoteric trivia, an anomaly astronomers might mention in passing and rarely investigate. The idea of dark matter retreated to the margins of physics and waited there, in the dark. It would wait for 40 years. Zwicky had shown that an invisible mass was needed to hold enormous clusters of galaxies together, but a cluster is a vast structure, an ocean holding thousands of separate islands. It left a natural question hanging. Does this invisible mass reach down into the individual galaxies themselves? Does the ghost only rule the deep spaces between galaxies, or is it also present inside the glowing disks where the stars and planets actually live? Answering that would take a different kind of instrument, and a different kind of person, someone patient enough to measure the faint edges of galaxies, one after another, and stubborn enough to trust what the measurements said. In the late 1960s, Vera Rubin was working at the Carnegie Institution of Washington. Rubin was quiet, meticulous, and deeply persistent. She had already spent years navigating a profession that did not want her in it. As a graduate student, she had been turned away from telescopes and dismissed at conferences. She had earned her doctorate at Georgetown, studying under the physicist George Gamow, and an early piece of her work, suggesting that galaxies were not scattered randomly but clumped together in the sky, had been brushed aside as an oddity. Later in her career, she had been refused observing time at the Palomar Observatory, in part because the dome had no women's restroom. She was accustomed to institutional resistance, and she had learned a particular kind of quiet response to it. She let the data speak, and she made the data unimpeachable. Rubin deliberately chose a project that would not draw her into a fight. Cosmology at the time was consumed by loud debates about quasars and the expansion of the universe. She wanted no part of those battles. She wanted solid, careful, observational work that no one could shout down. So she decided to study the rotation of spiral galaxies. A spiral galaxy, like our own Milky Way, is a great disk of stars turning around a dense, bright central core. Rubin set out to map exactly how fast the stars were moving at different distances from that core. To do this well, she needed better instruments than Zwicky had in 1933. She found them in the work of her colleague Kent Ford, an instrument builder who had designed a remarkably sensitive image tube spectrograph. Ford's device used photomultiplier tubes, a technology advanced heavily by the military for night vision. When faint light from the telescope entered the instrument, it struck a specialized surface that released electrons. Those electrons were accelerated and driven onto a phosphor screen, producing an image far brighter than the original light. This let Rubin and Ford do something new. Instead of taking a single, blurred average spectrum of a whole galaxy, they could take precise, localized spectra of specific regions, the velocity of the stars deep in the bright core, and separately, the velocity of the sparse, faint gas clouds out at the very edge of the disk. Their first major target was the galaxy Messier 31, Andromeda, our nearest large neighbor, roughly 2.5 million light-years away, a sprawling spiral holding perhaps 1 trillion stars. When they pointed the telescope at Andromeda, they had a clear expectation of what the data would show. They expected the galaxy to obey Johannes Kepler. In the early 1600s, Kepler worked out the laws describing how the planets orbit the Sun. In our solar system, almost all the mass sits in the center. The Sun alone holds 99.8% of the mass of the entire system. Because the mass is concentrated at the center, the gravitational pull weakens sharply as you move outward. To hold a stable orbit, a planet must balance its forward speed against that inward pull. A planet close to the Sun feels intense gravity and must move very fast to keep from falling in. Mercury orbits at roughly 47 kilometers per second. A planet far from the Sun feels weak gravity and must move slowly, or it will simply fly off into deep space. Neptune orbits at a leisurely 5.4 kilometers per second. If Neptune moved as fast as Mercury, the Sun could not hold it, and it would be gone. This is a Keplerian decline. The further you get from the central mass, the slower the orbit. Plot the speed against the distance, and the line falls away. In the late 1960s, astronomers universally assumed a spiral galaxy behaved the same way. Look at a photograph of Andromeda and almost all the light pools in the dense central bulge. Because light meant mass, they assumed almost all the mass pooled there too. A galaxy, in this picture, was simply a scaled-up solar system. The stars near the bright center should whip around at tremendous speeds. The stars out at the dim, sparse edges should crawl. The rotation curve had to fall away toward the rim. It was taken as a basic consequence of classical physics. Rubin and Ford spent night after night in the dome, capturing the faint light of ionized hydrogen far out at the edges of Andromeda, measuring the Doppler shifts point by point, working their way outward from the core to the rim. When Rubin finally plotted the results, the curve did not fall away. Near the center of Andromeda, the stars orbited at roughly 250 kilometers per second. Further out, past the bulge, into the thinner spiral arms, the speed held at 250 kilometers per second, and at the very edge of the visible disk, where the starlight faded into the blackness between galaxies, the isolated gas clouds were still moving at 250 kilometers per second. The rotation curve was flat. By Newton and Kepler, this was impossible. The gravity of the visible stars near the center of Andromeda was nowhere near strong enough to keep an object at the far edge from flying away at that speed. The outer disk should have been shedding stars like water flung from a spinning wheel, but it was not. The galaxy was intact. It was holding its shape. The only explanation the physics allowed was that the visible light was lying about where the mass was. The mass was not concentrated in the center. To keep the outer stars moving that fast without losing them, there had to be an enormous, invisible sphere of mass wrapped around the entire visible galaxy, its gravity reaching outward and holding the spinning edge in place. There is a precise and telling detail buried in the shape of that flat line. In ordinary physics, once you move past almost all of a galaxy's mass, the orbital speed should fall, because you are no longer gathering much additional mass as you move outward. The fact that the speed stays constant, mile after mile past the edge of the visible stars, carries a specific meaning. It means that as you move outward, the total amount of mass enclosed within your orbit keeps growing, steadily, even in regions where there are almost no stars left to account for it. The dark matter does not thin out where the starlight fades. It keeps going. There is roughly as much invisible mass in each successive shell of empty-looking space as there was in the last. The visible galaxy is not sitting at the edge of the dark matter. It is buried deep in the middle of a halo that extends far beyond anything we can see, and the further out Rubin's successors managed to measure, using faint gas clouds and radio emission far past the last star, the further the halo stretched. No one has ever cleanly found its outer edge. The galaxies simply fade into the dark long before the dark matter does. Rubin did not rush to announce that the universe was broken. She was too careful for that. She considered the possibility that Andromeda was an anomaly. Perhaps it had suffered a recent collision. Perhaps its magnetic fields were skewing her readings. So she loaded Ford's spectrograph back onto the telescope and looked at a different spiral. The rotation curve was flat. She looked at another. Flat. Across the 1970s, Rubin and Ford measured the rotation curves of 21 spiral galaxies, and eventually many more. Large galaxies and small ones. Tightly wound spirals and loose, ragged ones. Every single one had a flat rotation curve. Every visible disk was spinning too fast at its edge. Every galaxy was being held together by something that could not be seen. Around the same time, radio astronomers, tracing the same galaxies using the 21-centimeter emission line of neutral hydrogen, pushed the measurements even further out, past the visible starlight entirely, and found the curves stayed flat there too. The result did not depend on Rubin's particular instrument. It was simply true. When Rubin began presenting her findings, she did not meet the total silence Zwicky had faced, but she met a deep and stubborn reluctance. She later recalled distinguished astronomers telling her flatly that the data did not mean anything. They suggested her instruments were miscalibrated. They suggested she was misreading the Doppler shifts. The establishment did not want to concede that the stars they had spent centuries cataloguing were nearly irrelevant to the structure of the galaxies they belonged to. But the data would not yield. Ford's spectrograph was too accurate and Rubin's method too clean. The flat curves were real, and they were everywhere. Rubin spent the rest of her long career doing exactly this kind of quiet, decisive work, and using the standing it gave her to open doors for the women who came after her. She had entered a field that repeatedly told her she did not belong in it, and she left it changed, not through argument, but through the simple accumulation of measurements that could not be dismissed. She never received the Nobel Prize, a fact many of her colleagues considered one of the clearest oversights in the history of the award. She died in 2016. A few years later, a great new observatory in the mountains of Chile, built to survey the entire southern sky over and over in search of everything that moves and changes and flickers, was named in her honor. It is fitting that the instrument now carrying her name is designed, among many other things, to map the distribution of dark matter across the sky more finely than anything before it. The woman who first proved the invisible halos were wrapped around every galaxy has an observatory devoted, in part, to charting the very thing she found. There is something worth noticing about the pattern that connects Zwicky and Rubin, twice, 4 decades apart. And a careful measurement revealed the same impossible fact that galaxies and clusters contain far more mass than their light can account for. Twice, the measurement was correct. And twice, the community was slow to believe it, not because the mathematics was weak, but because the conclusion was uncomfortable. The lesson is not that scientists are foolish. It is that a genuinely strange result has to survive a period of disbelief before it is accepted, and that the survival depends on the data being unimpeachable. Zwicky's data in 1933 was suggestive but rough. Rubin's, 40 years later, was overwhelming. The idea did not win because the universe changed. It won because the measurements finally became impossible to wave away. What Rubin proved in the 1970s was larger than a confirmation of Zwicky. She showed that the ghost was not only lurking in the deep spaces between clusters, it was wrapped intimately around our own home. When you look at an image of a spiral galaxy, you are conditioned to read it as a self-contained object, a disk of stars floating in empty dark. Rubin's data revealed that this is an illusion. A visible galaxy is not an independent object. It is a bright, flat smudge sitting deep inside the center of an enormous spherical halo of dark matter. That invisible halo extends far beyond the reach of the starlight. It is many times wider than the visible disk, and it holds several times more mass. The glowing spiral we point at and call a galaxy is only the luminous debris that has settled into the very bottom of the dark matter's gravitational well. This shifts the weight of things. If the invisible halo is larger and heavier than the galaxy it contains, then the galaxy is not the main structure. The halo is the main structure. The stars are an accessory. And that leads to the most disquieting consequence of the flat curves. It is a fact about order, about who arrived first. You exist because the dark matter went first. In the extreme early universe, shortly after the Big Bang, the cosmos was a blindingly hot, dense plasma of expanding energy and elementary particles. As it expanded, it began to cool. But ordinary matter, the protons, the electrons, the hydrogen gas was still far too hot, moving too fast, bathed in too much radiation, to clump together. Every time ordinary matter began to gather under its own gravity, the heat and the pressure of the trapped photons blew it apart again. Ordinary matter was locked in a state of chaotic, expanding static, unable to build anything. If the universe had contained only ordinary matter, it would have expanded into a thin, featureless haze of gas and stayed that way. No star would have ignited. No galaxy would have spun. No planet would have formed. There would have been no structure at all. But dark matter was there. And dark matter does not interact with light. It feels no radiation pressure. It is blind to the photons that were tearing the ordinary matter apart. Because it was immune to the light, the dark matter could slow down and cool long before ordinary matter could. It settled out of the early chaos first, and once it had settled, its gravity took over. It began to draw itself together, pulling more and more invisible mass into growing concentrations, sinking deep gravitational wells into the fabric of the expanding universe, and stringing an invisible scaffolding across it. Much later, when the universe had expanded far enough for the ordinary matter to cool, the hydrogen gas stopped fighting itself. And when it did, it found the void was no longer empty. The scaffolding was already standing. The trenches were already dug. The gas had no choice. It was pulled down into the centers of the dark matter halos that were waiting for it. As it fell, it compressed and heated and ignited into the first stars. Those stars gathered into the first disks. Those disks became the galaxies. Every star in the night sky, every planet turning around those stars, every atom of iron in your blood, exists because the dark matter built the architecture first and let the visible world assemble inside it. We are the after effect of a ghost's gravity. That raises the next question on its own. If every visible thing sits inside an invisible halo, and these halos predate the stars, then how did they arrange themselves? A universe that began almost perfectly smooth should have stayed smooth. Something had to break the symmetry and decide where the scaffolding would rise and where it would not. To see how that happened, we have to look at the geometry of the extreme early cosmos. In the beginning, the universe was incredibly dense, blindingly hot, and almost perfectly uniform. Take a cubic light year of space from one side of the newborn universe and compare it to a cubic light year from the far side, and they would look identical, the same energy, the same temperature, the same spread of particles, almost identical, not quite. Buried in that expanding fog were microscopic irregularities. These were quantum fluctuations, tiny, random variations in energy density that existed at the subatomic level in the first fractions of a second. As the universe passed through a phase of violent expansion known as inflation, these subatomic variations were stretched out to enormous scales, until they became faint imperfections in the distribution of matter across the whole cosmos. In some regions, the universe was perhaps 1 part in 100,000 denser than average. In others, 1 part in 100,000 thinner. That period of violent expansion is worth dwelling on, because it solved a puzzle that had troubled cosmologists for years, and it explains why the early universe was so extraordinarily uniform in the first place. When astronomers measured the temperature of the oldest light coming from opposite sides of the sky, they found it almost exactly the same, to within that 1 part in 100,000. This is stranger than it sounds. Those two regions, on opposite sides of our view, are so far apart that light could never have travelled between them in the age of the universe. They have never been in contact. Nothing could have passed from one to the other to even them out. So how did they arrive at precisely the same temperature, as though they had once agreed on it? The answer inflation provides is that, in the very first instant, before the violent expansion, the entire observable universe was packed into a region far smaller than an atom, small enough that every part of it was in contact, able to settle into a common temperature. Then, in a fraction of a second, that tiny, uniform patch was stretched to enormous size, carrying its uniformity with it and freezing in the microscopic quantum fluctuations as it went. Everything we see, the entire cosmic web across billions of light years, grew from the stretched-out imperfections of a patch that was once smaller than a single particle. The largest structures in existence are the fossilized echoes of the smallest possible ripples. That tiny discrepancy was all gravity needed. Gravity, at its core, is an amplifier of imperfection. In a perfectly smooth universe, it would pull equally in every direction, and nothing would ever form. But because those stretched fluctuations existed, the slightly denser regions pulled slightly harder than their surroundings. Because they pulled harder, they gathered more dark matter. Because they gathered more mass, they pulled harder still, reaching out to draw in dark matter from even further away. It was a runaway process. Over hundreds of millions of years, the dark matter slowly abandoned the thinner regions and flowed, like an invisible river, toward the regions that were already dense. And because dark matter does not feel the electromagnetic friction that makes ordinary gas crash and heat and resist, it could flow and collapse freely long before the hydrogen was able to. But it did not collapse into isolated spheres. The mathematics of gravity acting on a vast, expanding fluid produces a different shape entirely. The dark matter collapsed into a network. There was a real argument through the 1970s and 80s about how the network actually assembled itself, and the argument turned out to hold a clue about what the dark matter was made of. One camp imagined a top-down process. In this picture, the largest structures formed first enormous flattened sheets of collapsing matter that some theorists called pancakes, which then fragmented into smaller pieces, breaking down into clusters and finally into individual galaxies. The other camp imagined the opposite, a bottom-up process in which the smallest clumps formed first, and these small clumps gradually merged and accumulated into ever larger structures, building galaxies before clusters and clusters before superclusters. The two pictures made different predictions about the order in which things appeared, and about the fine detail of the web. The deciding factor was speed. If the dark matter particles had been light and fast-moving in the early universe, streaming along at close to the speed of light, they would have smeared out all the small-scale structure, erasing the little clumps and leaving only the largest sheets to form first, the top-down picture. If instead the particles were heavy and slow, they would have settled quietly into the smallest wells first, and structure would have grown from the bottom up. When astronomers looked at the real universe, at the actual sizes and ages of galaxies, at the way small galaxies clearly existed very early, the bottom-up picture won. And that told them something specific about the ghost. The dark matter had to have been moving slowly in the early universe. It had to be, in the language physicists adopted, cold. Not cold in temperature, but cold in motion. Slow enough to fall into the smallest wells and stay there. This single word, cold, would become central to everything that followed, because it ruled out entire categories of candidate particle before anyone had built a single detector. If you could step outside the universe and look at it from an impossible distance, it would not resemble a random scatter of galaxies. It would look like a sponge. It would look like the branching pathways inside a brain. Astronomers call it the cosmic web. It is built from immense, branching filaments of dark matter, some of them stretching across hundreds of millions of light years. These invisible filaments are the highways of the universe. When ordinary matter finally cooled enough to form stars, it was drawn down into them, and the galaxies we see today are strung along these threads like beads of light on a wire. Where two or more massive filaments cross, the gravity becomes overwhelming. These intersections are the nodes of the web, the deepest wells in the cosmos, and this is where the great clusters form. When Fritz Zwicky measured the Coma cluster in 1933 and found its galaxies moving too fast, he was, without knowing it, standing at one of these intersections watching thousands of galaxies caught in the cross-currents of merging dark matter filaments. But the web is defined just as much by its emptiness. Because gravity had to gather the dark matter from somewhere, the regions it drained became truly empty. These are the cosmic void's immense, near-spherical regions, hundreds of millions of light-years across, from which the dark matter has been swept toward the surrounding filaments, and from which the ordinary matter has followed. One of the largest known is the Boötes void, discovered in 1981, lying nearly 700 million light-years from Earth. It is roughly 330 million light-years across. To feel that scale, consider that the Milky Way and Andromeda, our nearest large neighbour, are only 2.5 million light-years apart. The Boötes void could swallow that gap more than 100 times over, and it holds almost nothing. It is so vast and so empty that if the Milky Way had formed at its centre, our astronomers would not have known other galaxies existed until well into the 20th century. Our entire history of looking up would have been spent staring into a black, featureless horizon, never suspecting the web that surrounded us. We do not live in a void, we live on the web. You are lying in a room on a planet called Earth. The Earth orbits a yellow dwarf star. That star drifts through the Orion arm of the Milky Way. The Milky Way belongs to a small, gravitationally bound family of roughly 50 galaxies called the Local Group. But the Local Group is not at rest. It is being drawn toward a far larger structure, the Virgo Cluster, which holds thousands of galaxies. And the Virgo Cluster, together with our Local Group, is only a single appendage of something larger, still an immense branch of the cosmic web. Zoom back in from that vastness to our own galaxy, and the dark matter is just as present and just as invisible. The Milky Way, the disk of a few 100 billion stars that we live inside, is cradled in a roughly spherical halo of dark matter that dwarfs it. If you could see the dark matter, the bright spiral of stars we call our galaxy would be only a small, flat, glowing lens sitting at the center of an enormous invisible sphere, many times wider and several times heavier. The stars are the visible sediment, the halo is the galaxy. And that halo does not sit still. It has a structure of its own, revealed by the objects trapped within it. Scattered around the Milky Way are dozens of small satellite galaxies, faint dwarf galaxies containing only a handful of stars compared to our own. When astronomers measure how fast the stars in these dwarfs are moving, they find something remarkable. Some of these tiny galaxies are almost entirely dark matter. In the most extreme cases, for every unit of visible starlight, there are hundreds of units of invisible mass. They are less like galaxies with some dark matter, and more like clumps of dark matter with a faint sprinkling of stars caught inside. They are, in a sense, the purest dark matter objects we know of. Our own galaxy obeys the same rule Rubin found in Andromeda, and it is worth making that personal for a moment, because it includes you. The Sun is not sitting still at the center of the Milky Way. It lies far out in the disk, roughly 2/3 of the way from the center to the visible edge, and it is orbiting the galactic core at a little over 200 kilometers per second, carrying the Earth and everything on it along with it. At that speed, it takes the Sun something like 230 million years to complete a single lap of the galaxy, so long that the last time the Sun was in its current position, in its orbit, the earliest dinosaurs were only beginning to appear on Earth. And here is the point. At that distance from the center, moving at that speed, the Sun should not be gravitationally bound to the galaxy at all, if the only mass present were the mass we can see. The visible Milky Way is not heavy enough to hold its own Sun in orbit. We stay bound because we, too, are deep inside a dark matter halo, held in place by the gravity of a mass we cannot see and have never touched. The flat rotation curve is not something that happens to distant galaxies. It is happening to you right now, as you are carried around the center of the Milky Way by the pull of the invisible. The halo tells its history in another way too. When one of these small dwarf galaxies wanders too close to the Milky Way, the tidal pull of our galaxy's gravity slowly tears it apart, stretching its stars into a long, thin ribbon that wraps around the sky. Astronomers have found many of these stellar streams, the shredded remains of galaxies and star clusters that the Milky Way has consumed over billions of years. And because each stream traces the exact path its stars are following through the halo, and because that path is shaped by gravity, the streams act as delicate probes of the invisible mass. By mapping how a stream bends and where it thins, astronomers can feel out the shape of the dark matter halo it is moving through, and even detect the gravitational wakes left by smaller invisible clumps the stream has passed near. We are reading the shape of the ghost by watching the wreckage of the galaxies it has swallowed, and it is not somewhere far away. The dark matter halo of the Milky Way passes directly through the solar system, directly through the Earth, directly through the room where you are lying. At the distance of the Sun from the galactic center, the density of dark matter is estimated to be small but real, very roughly the mass of a single proton in every few cubic centimeters of space. That sounds like almost nothing, but because the Earth is moving through this halo at hundreds of kilometers per second, an enormous flux of it sweeps through you constantly. This is the silent rain from the beginning of the night. It is not a metaphor. It is a measured, physical estimate of how much invisible mass is passing through your body while you rest. In 2014, a team of astronomers mapped the velocities of thousands of galaxies in our local region, tracing how each one moved and following the gravitational currents pulling them along. They discovered that the Milky Way, the Virgo cluster, and 100,000 other galaxies are all flowing along the same great dark matter structure, all sliding toward the same central basin. They named this supercluster Laniakea, a Hawaiian word meaning immense heaven. Laniakea spans some 520 million light-years and contains the mass of about 100 million billion suns. And even Laniakea is only one thread in the greater web that fills the observable universe. You are suspended in an invisible current. The room you are in, the planet you are on, and the galaxy you belong to are all in constant motion, sliding down the gravitational trench of a dark matter filament that was laid into place billions of years before the sun first burned. We know this architecture exists in more than one way. The great supercomputer simulations that run the physics of gravity forward from the Big Bang projects, like the Millennium simulation, which followed billions of particles across the model universe, reproduce the cosmic web in exact detail. The same filaments, the same nodes, the same voids, and decades earlier, when astronomers first began systematically measuring the distances to thousands of real galaxies, mapping surveys revealed enormous coherent structures in the actual sky, walls and filaments and empty regions, matching what the mathematics demanded. The model and the sky agree. The first of these surveys, carried out in the 1980s, produced one of the most quietly startling images in the history of astronomy. The team plotted the positions of a few thousand galaxies in a thin wedge of sky, expecting the dots to scatter more or less evenly. Instead, the galaxies arranged themselves along thin curving strands, wrapped around great empty circles, so that the whole picture looked less like a random spray and more like the outline of a human figure with arms outstretched. Astronomers half-jokingly called that pattern the stickman. Running through it was a vast sheet of galaxies stretching across a substantial fraction of the observable sky, which they named the Great Wall. It was, at the time, the largest known structure in the universe, and it was clearly not a fluke of statistics. The galaxies were strung along invisible filaments, exactly as the dark matter theory required. Later and deeper surveys found still larger walls, one of them stretching well over 1 billion light-years, and each one reinforced the same conclusion. On the largest scales, the universe is not a smooth scattering, it is a web. Our own local motion tells the same story from the inside. The Milky Way is not drifting through the void at random. For decades, astronomers have known that our galaxy, along with everything near it, is being pulled toward a particular region of the sky by a great concentration of mass, a region so massive it was simply named the Great Attractor, even before anyone could see clearly what lay there, because much of it sits hidden behind the crowded band of our own galaxy's disk. And when the team that mapped Laniakea traced the local currents in fine detail, they found that our motion is shaped not only by what is pulling us, but by what is pushing us. On the opposite side of the sky from the Great Attractor lies an unusually empty region, a great underdensity, and because it contains less than the average amount of matter, it effectively repels us. We drift away from the emptiness toward the fullness. They called it the dipole repeller. We are being pulled toward mass on one side and pushed from a void on the other, sliding along the gravitational contours of a structure written entirely in dark matter. It is worth understanding how those simulations are actually built, because they are one of the strongest pieces of evidence that our picture is right, and one of the places where honest cracks still show. To simulate a universe, cosmologists do not model every star or atom, there are far too many. Instead, they fill a virtual box, meant to represent an enormous cube of the cosmos, with billions of particles, each one standing in for a vast quantity of dark matter. They set the box in the state the early universe was in, smooth almost everywhere, with the same faint imperfections the oldest light reveals. Then they let a computer calculate the gravitational pull of every particle on every other, step the whole system forward in time by a small amount, and repeat, again and again, billions upon billions of times, compressing 13 billion years of cosmic evolution into weeks of computation on some of the largest machines ever built. And when the simulation finishes, when the virtual universe has aged to the present day, the particles have arranged themselves, entirely on their own, into filaments and nodes and voids. They have built a cosmic web that looks, in statistical detail, exactly like the one we see in the sky. No one puts the web in by hand. It emerges from nothing but gravity acting on cold dark matter, and that agreement is powerful evidence that the ingredients are correct. But the picture is not flawless, and this is where a careful listener should stay awake. When the simulations are pushed down to the smallest scales, to the level of individual galaxies and their immediate surroundings, some of their predictions do not perfectly match what astronomers observe. The simulations tend to predict that large galaxies like ours should be swarmed by more small satellite galaxies than we actually find. They tend to predict that the dark matter should pile up into a sharp, dense spike at the very center of a galaxy, while some observations suggest a gentler, flatter core instead. These mismatches have names, and they have been argued over for years. They may well be resolved by the messy physics of ordinary matter, the winds and explosions of stars blowing gas around and reshaping the centers of galaxies in ways the simplest simulations leave out. Or they may be hinting at something we do not yet understand about the dark matter itself. This is the honest state of the field. On the largest scales, the theory of cold dark matter is triumphant. On the smallest scales, there are loose threads, and no one is entirely certain yet where they lead. But a simulation is still only mathematics running on silicon, and a galaxy survey maps where the light is, not where the invisible mass is. If this scaffolding truly spans the physical cosmos, we need to prove its shape directly. We need a way to look across the void and trace the outline of a thing that gives off no light of its own. We do it by watching what it does to light that passes nearby. To understand how you can see the invisible, you first have to change what you think gravity is. For more than 2 centuries after Isaac Newton, gravity was understood as an invisible tether, a mysterious pull reaching across empty space, the sun tugging on the earth tugging on the moon. Space itself was just the empty stage on which the pulling happened. In 1915, Albert Einstein rebuilt the stage. With his theory of general relativity, he proposed that space is not an empty backdrop at all. Space and time are woven into a single physical medium, a 4-dimensional fabric. And gravity is not a tether pulling objects across that fabric. Gravity is the bending of the fabric itself. When mass exists, it warps the space and time around it, and the heavier the mass, the deeper the warp. The Earth orbits the Sun not because a rope connects them, but because it is following the curved depression that the Sun's mass has pressed into the surrounding space. This geometric picture of gravity leads to a very specific, testable prediction. Light has no mass. Under Newton's physics, gravity should not touch it at all. But under general relativity, light must travel through space, and if that space is curved, the light has no choice but to follow the curve. In 1919, the British astronomer Arthur Eddington sailed to the island of Principe off the coast of West Africa to test this idea during a total solar eclipse, while a second team travelled to Brazil to do the same. As the moon covered the blinding face of the sun and the sky went dark, the stars that lay directly behind the sun became briefly visible. Eddington photographed them and compared their apparent positions to photographs of the same stars taken at night when the sun was elsewhere. The stars had shifted. Their light, grazing the edge of the sun on its way to Earth, had fallen into the curved space around it and bent, arriving slightly out of place. Mass bends space, and bent space bends light. Einstein was right. The sun is a single star. It produces a small, measurable bend. But suppose the mass doing the bending is not one star but a dark matter halo 1 trillion times heavier. Then it becomes a lens on a cosmic scale. Imagine a photon leaving a bright, distant galaxy 10 billion years ago. It sets off across the expanding void in a straight line through flat space. Halfway through its journey, it approaches a great node of the cosmic web, a galaxy cluster embedded in an enormous concentration of dark matter. The dark matter does not absorb the photon or reflect it, but its sheer mass has warped the surrounding space into a deep funnel, millions of light years wide. Entering that funnel, the photon must follow the geometry. Its straight line becomes a curve. It sweeps around the invisible mass and continues on. 5 billion years later, it lands on the mirror of a telescope on Earth. And when astronomers look at the image that photon helped form, they do not see the distant galaxy as it truly is. They see a distortion, because the dark matter acted as a warped, imperfect magnifying glass. The image of the background galaxy is stretched, smeared, and brightened. This is gravitational lensing. When the alignment of Earth, the dark matter, and the background galaxy is nearly perfect, the result can be extraordinary. The light of the distant galaxy is bent evenly around every side of the invisible mass, and in the telescope it appears as a glowing ring of ancient light encircling the foreground cluster. Astronomers call these Einstein rings a name with a certain irony, since it was Zwicky, not Einstein, who first argued that galaxies would produce lensing bright enough to observe. In other cases, the warped space splits a single background galaxy into several separate images, 4 or 5 identical copies of the same object arranged around the center of the dark matter well, like reflections around the rim of a curved mirror. The first such lensed object, a double image of a single distant quasar, was identified in 1979, and it opened a new way of weighing the universe. There is a small human story folded into how this prediction reached the world. Einstein had worked out the mathematics of one star bending the light of another as early as 1912, but he set it aside, convinced the effect was far too small ever to be seen. 2 decades later, an amateur enthusiast named Rudi Mandl showed up and pressed him to publish it. Einstein obliged, writing a short paper in 1936, and he added, almost apologetically, that there was no great hope of observing the phenomenon directly. He was right about single stars and wrong about the universe at large. It was Fritz Zwicky, the following year, who pointed out that entire galaxies and clusters, being so much more massive, would bend light strongly enough to be seen, and who suggested that lensing could one day be used to weigh those clusters and to search for the very dark matter he had proposed. It took another 40 years for the technology to catch up with him, as it so often did. When astronomers finally turned this tool on the great clusters, the images were extraordinary. Point a powerful telescope at one of the most massive known clusters and you see, threaded around its center, dozens of thin, luminous arcs, the smeared, stretched images of galaxies lying far behind it, their light bent into slivers by the cluster's gravity. By measuring the precise shape and position of every arc, astronomers can reconstruct the distribution of mass in the cluster in fine detail, and they find, every time, that most of that mass is not in the visible galaxies. It is in the invisible halo enveloping them. The arcs are, in effect, a portrait of dark matter drawn in the borrowed light of more distant things. In recent years, this has been scaled up into something like a census of the invisible. Large surveys, first from the ground and now from a dedicated space telescope built specifically to measure the faint shearing of distant galaxies across enormous swaths of the sky, have begun producing sprawling maps of where the dark matter lies. These maps do not show galaxies. They show mass-great ridges and clumps and filaments of it, glowing on the map wherever the background light has been most stretched, dark wherever the voids fall away. It is the closest thing we have to a photograph of the scaffolding, and it was assembled entirely from starlight that happened to pass nearby. There is a further gift hidden in all this bending, one that astronomers have learned to exploit. A lens does not only distort, it also magnifies. When a great cluster of dark matter warps the space around it, the light of a galaxy lying far behind is not merely stretched into an arc, it is amplified, brightened, made larger and easier to see than it otherwise would be. This means the most massive dark matter concentrations in the sky double as natural telescopes, vast gravitational lenses that nature has placed between us and the deep past. By pointing our own instruments through the center of such a cluster, astronomers can see galaxies far too faint and far too distant to observe by any other means. Galaxies from the early universe, whose light would be hopelessly dim if it had traveled to us in a straight line, but which the cluster's gravity has magnified into visibility. Some of the earliest galaxies ever detected, formed when the universe was only a small fraction of its present age, were found precisely this way. Their ancient light gathered and focused by an invisible mass, sitting billions of light years closer to home. The dark matter, which gives off no light of its own, has become one of our most powerful tools for collecting the light of everything behind it. We are using the ghost as a lens to see the dawn of the cosmos. This is strong lensing, and it happens only when the alignment is nearly exact near the densest nodes of the web. To map the scaffolding across the broader universe, astronomers rely on something far subtler and far harder to measure: weak lensing. As light crosses the universe, Almost all of it passes some amount of dark matter along the way. It is not bent into rings or split into copies. It is simply sheared, stretched by perhaps 1 or 2% in the direction of the unseen mass. Look at a single distant galaxy that appears slightly elongated, and you cannot know whether it was born that way or stretched in transit. The distortion is too small to read on any single object. But take a deep image of the sky containing 100,000 faint galaxies, measure the shape of every one, and the statistics give up the secret. If the galaxies across one region are all stretched slightly in the same direction, that is not chance. It is the fingerprint of a dark matter filament lying between them and us, warping the space their light had to cross. Reading this requires enormous patience. There is no single moment at an eyepiece. It is years of supercomputers analyzing the 1% distortions in the shapes of millions of faint galaxies, calculating exactly how much mass is needed to produce that degree of shearing, and exactly where that mass must sit. Through this method, across surveys covering large fractions of the whole sky, astronomers have reverse-engineered the invisible. They have drawn three-dimensional maps of the dark matter web, plotting the great halos, the connecting filaments, and the empty voids. And the maps drawn from bent light match the maps produced by the simulations of the early universe. The ghost has a defined shape. We know where the filaments run, we know where the nodes are heavy, we know where the voids fall away. We are using the oldest light in the universe to trace the outline of a substance that will not touch light at all. It is a shadow play, written in the faint stretching of galaxies billions of light years away. It is worth stepping back to see how the case became overwhelming, because no single measurement did it. What changed between Zwicky's dismissed paper and the modern consensus was not one decisive experiment, but a convergence. By the end of the 1970s and into the 80s, entirely separate lines of evidence, using entirely different instruments and assumptions, had all begun demanding the same invisible mass. Rubin's flat rotation curves said the individual galaxies were too heavy. The motions of galaxies within clusters, exactly the measurement Zwicky had pioneered, said the clusters were too heavy. And when astronomers returned to the Coma cluster with modern tools, they confirmed what he had claimed in 1933, that the overwhelming majority of its mass is dark. The hot X-ray gas discovered filling those same clusters could only be held in place, rather than boiling away into space, if there were far more gravity present than the visible galaxies could supply. And the first serious computer simulations of how galaxies form found that a universe of ordinary matter alone simply could not build structure fast enough to match the sky, while a universe seeded with cold dark matter could. When 4 completely independent methods, resting on 4 completely different sets of physics, all point to the same missing mass in the same amount, the situation changes. A single anomaly can be a measurement error. A single strange galaxy can be a fluke. But when the rotation of galaxies, the motion of clusters, the behavior of hot gas, and the growth of cosmic structure all demand the same invisible substance, the idea stops being an anomaly and becomes the framework itself. That is what happened. Somewhere in those 2 decades, dark matter moved from the far margins of physics, where Zwicky had left it, into the center of cosmology, where it now sits as one of the foundations of our entire picture of the universe. Not because anyone wanted to believe in an invisible substance, but because too many separate roads led to the same place. The maps are precise, the mathematics is consistent, but every part of this, the weighing of Coma, the flat rotation curves of Andromeda, the shearing in the deep fields, rests on one assumption that we have not yet examined. It assumes that our theory of gravity is correct, and there is a version of this story in which there is no dark matter at all, in which the invisible ocean is a mistake, and gravity itself simply behaves differently than we think at the faint edges of galaxies. Before we go looking underground for particles, that possibility deserves a hearing, because physics has been fooled in exactly this way before. Physics has an uncomfortable, rarely advertised history of inventing invisible things to rescue its equations. When an observation refuses to match an established formula, the first instinct is not to discard the formula. The first instinct is to assume something unseen is hiding in the room, making the numbers work. In the 19th century, astronomers tracked the orbit of Uranus and found it was not moving quite as Newton's laws predicted. It lagged, as though something were tugging it off course. Rather than abandon Newton, the French mathematician Urbain Le Verrier proposed that an undiscovered planet lay further out in the dark, and he calculated exactly where it should be. Astronomers pointed their telescopes at that precise spot and found Neptune close to the predicted position. The equations were saved by finding the invisible thing. A few years later, Le Verrier turned to the inner solar system. He noticed that the orbit of Mercury was also slightly wrong, wobbling in a way Newton could not fully account for. Emboldened by his triumph, he proposed another unseen planet, this one orbiting between Mercury and the Sun. He even named it. He called it Vulcan. For the next 50 years, astronomers searched for Vulcan, straining to glimpse it in the glare during eclipses, certain that the missing mass would rescue classical physics once again. They never found it. Vulcan did not exist. The wobble in Mercury's orbit was not caused by a hidden planet. It was caused by the fact that Newton's laws, for all their success, were incomplete. They worked beautifully across ordinary distances, and they broke down in the intense gravity near the Sun. It took Einstein and general relativity to explain Mercury's motion without inventing anything at all. In 1983, a physicist named Mordechai Milgrom, working at the Weizmann Institute in Israel, looked at the flat rotation curves Rubin had found, and at the massive, invisible halos the field had embraced to explain them, and he asked whether astronomy was chasing another Vulcan. He asked a simple and profoundly disruptive question. What if we are inventing a ghost to save Isaac Newton, when we should be rewriting the law of gravity? Newton's law of gravitation rests on an inverse square relationship. As you move away from a mass, the pull weakens with the square of the distance. Double your distance and the gravity does not halve, it falls to a quarter. Triple it and it falls to a ninth. This law has been tested exhaustively. It governs the fall of an apple, the orbit of the moon, and the path of every space probe ever launched. But Milgrom noticed a blind spot. Newton's law had only ever been verified in places with reasonably strong gravity. Even the outer planets feel a firm pull from the Sun. At the extreme edge of a spiral galaxy, where Rubin had measured stars moving at 250 kilometers per second, the gravitational acceleration is almost inconceivably weak, a tiny fraction of a billionth of the acceleration you feel standing on Earth. A star out there is barely feeling the whisper of the galaxy's mass. Milgrom pointed out that human beings had never actually tested how gravity behaves at such vanishingly low accelerations. We had simply assumed the inverse square law held all the way down. He proposed an alternative, which he called modified Newtonian dynamics. The idea was elegant. Gravity works exactly as Newton described, right up until the acceleration falls below a specific, incredibly small threshold. Below that threshold, the rule changes. The inverse square law gives way to a gentler relationship, and gravity stops weakening so quickly with distance. It holds on harder across greater distances than classical physics allows. When Milgrom applied his modified equation to Rubin's data, the results were remarkably clean. Without adding a single gram of dark matter, without invisible halos or a cosmic web, his modification reproduced the flat rotation curves of spiral galaxies. The stars at the edge of Andromeda were moving fast. In this picture, not because an unseen mass was pulling them, but because gravity itself naturally tightened its grip in that faint regime. It even predicted, in advance, a tight relationship between the brightness of a galaxy and its rotation speed that astronomers do in fact observe. For a while, the theory offered a genuine lifeline to physicists, deeply uneasy with the idea that most of the universe was made of an untouchable substance. It was clean. It required no new particles, no underground detectors. It asked only that we admit our centuries-old equation was slightly imperfect at the edge of our knowledge. But science is a ruthless environment. For a new theory of gravity to survive, it cannot solve only one problem. It has to solve all of them. It has to account for the rotation of galaxies, the bending of light, the collision of clusters, and the structure of the early universe at once. This is where the modification began to fail. Apply Milgrom's idea to the bullet cluster, the wreckage where the gas slowed and the mass coasted through, and the mathematics breaks. If there is no dark matter, and gravity is simply a property of the visible material, then the lensing should be centered on the pink superheated plasma, because that is where most of the ordinary matter is. The mass and the gas should sit in the same place, but the telescopes clearly showed them pulled apart. A modified law of gravity cannot explain a source of gravity that detaches from its own matter and flies away. Something has to be carrying that gravity through the collision, invisibly, and that something can only be mass. The modification also failed to produce the intricate, three-dimensional structure of the cosmic web, and most decisively of all, it could not reproduce the pattern in the oldest light in the universe, the fossil record of the early cosmos, which we will come to shortly, and which requires a specific quantity of matter that does not interact with light. Physicists built more sophisticated relativistic versions of the theory to try to close these gaps. One of the most serious attempts wrapped Milgram's simple rule inside the full machinery of curved space and time, adding extra fields to carry the modified gravity in a way consistent with Einstein. It was an impressive piece of work, and it could reproduce some of the lensing that the original simple version could not. But it was elaborate, and it still could not reproduce everything, not the detailed pattern of the oldest light, and not the full behavior of galaxy clusters. Each version had to strain harder and add more machinery to survive. Over the decades, the consensus settled firmly against modified gravity as a complete replacement. The evidence for dark matter as a real, physical substance simply grew too heavy to lift. And yet, it would be dishonest to say the idea was simply wrong and leave it there, because at one particular scale it works uncannily well. When astronomers plot for a large sample of galaxies, the acceleration they actually observe against the acceleration that the visible matter alone should produce, the points do not scatter into a cloud. They fall along a single tight line with almost no spread. In the standard picture, this is a little surprising. It means the invisible dark matter in every galaxy is somehow arranged in lockstep with the visible matter, following the same relationship in a dwarf galaxy and a giant spiral alike. Milgram's rule predicts that tight line directly, with no adjustment, as a simple consequence of his modified law. This is the reason a small, serious group of physicists still works on modified gravity today. Not because they think it explains the whole universe, it plainly does not, but because it captures something real about the behavior of individual galaxies that the dark matter picture has to work harder to reproduce. And an honest scientist does not ignore a clue merely because it is inconvenient. The deepest trouble for modified gravity is that it does not solve its own problem cleanly. To make the numbers work in galaxy clusters, the modified theories usually have to reintroduce some unseen mass. Anyway, a little dark matter smuggled back in through the side door, a theory invented specifically to abolish dark matter that ends up needing dark matter has lost its central advantage. That, more than anything, is why the field moved on. But the tight line remains, sitting in the data, quietly insisting that whatever the full answer is, it will have to explain not only where the dark matter is, but why it tracks the visible matter so faithfully in every single galaxy we can measure. But Milgram's challenge earned its place in the history of this subject, and it is worth being honest about why. It is a lonely thing to stand against your entire discipline. Milgram watched a community rapidly accepting an invisible, undetectable substance that made up most of reality, and he insisted they check their oldest assumption before they did. He was, in the end, almost certainly wrong that dark matter is an illusion, but he was right to make physics prove it. A universe that is mostly invisible is a strange thing to accept, and it should never be accepted merely because stress testing Newton felt like too much trouble. We accept it now not because we wanted to, but because every alternative was tried, and every alternative came up short. So the invisible mass is real. It is physical. The halos are physical, the web is physical, and the silent rain passing through your room tonight is physical. Which forces the question that particle physics has spent 40 years and billions of dollars trying to answer. If it is real, what is it actually made of? To answer that, the scale of the inquiry has to collapse. We have to leave the clusters and the lenses and the great web behind, put down the telescopes, and look instead at the microscopic architecture of reality, at the chalkboards of theoretical particle physics. By the late 20th century, physics had assembled a masterpiece known as the Standard Model. It is arguably the most successful scientific theory ever devised. The Standard Model catalogues every known fundamental particle. It lists the quarks that build the protons in your body, the electrons that carry the signals through your nerves, the photons that carry light, and the neutrinos that stream out of the core of the sun in numbers beyond counting. It is a nearly complete inventory of the visible, tangible world, confirmed to astonishing precision. The scale of that precision is difficult to overstate. The Standard Model is not a rough sketch. It is a framework that has predicted the outcomes of experiments to more decimal places than almost any theory in the history of science, sometimes agreeing with measurement to 11 or 12 digits. It organizes all of ordinary matter into a small, elegant set of building blocks, a handful of quarks, which combine to form the protons and neutrons in every atomic nucleus, and a handful of lighter particles, including the electron and the neutrino. It describes 3 of the 4 fundamental forces that govern how these particles behave, and it does so with a mathematical consistency that took the better part of a century to assemble. Its final missing piece, a particle that gives the others their mass, was predicted decades before it was found, and when a vast machine finally produced it, it appeared almost exactly where the theory said it would. By any reasonable standard, the Standard Model is one of the crowning achievements of human thought. It is a nearly finished map of everything you have ever touched, and that is precisely what makes its silence on dark matter so striking. Here is a theory that accounts, to exquisite precision, for every particle we have ever detected in a laboratory. And it has nothing whatsoever to say about 85% of the matter in the universe. The most successful theory in physics describes only the thin, luminous minority of what exists. It is a complete and beautiful account of the exception, but dark matter is not on the list. Nothing in the Standard Model has the specific combination of properties the ghost requires. To build the invisible scaffolding of the cosmos, a particle has to satisfy 3 demands at once. It must have mass, so it can supply gravity. It must be stable, so that it does not decay into other particles, and can survive for the 13.8 billion years since the Big Bang. And it must not feel the electromagnetic force, so that it never emits, absorbs, or reflects a single photon. No known particle fits. The neutrino comes closest. It is stable and ignores light, but it fails on 2 counts. It is almost unimaginably light, and in the early universe it moved at nearly the speed of light. Physicists call this hot dark matter, and hot dark matter cannot build the cosmic web, moving that fast. Neutrinos would have streamed straight out of the young gravitational wells rather than settling into them, smearing structure out rather than seeding it. The web we see requires dark matter that moved slowly in the early universe, cold, dark matter, able to sink into the wells and stay. For a while, there was hope that the missing mass might be ordinary after all, just hidden in dark, dense objects, burnt-out stars, isolated black holes, rogue planets drifting between the stars. Physicists gave these hypothetical objects a name, calling them massive compact halo objects. Through the 1990s, several teams searched for them using a clever technique. If such an object drifted in front of a distant star, its gravity would briefly focus the starlight and make the star flare up, a small, predictable brightening lasting days or weeks. The teams monitored millions of stars for years, watching for these telltale flares. They found some, but nowhere near enough. The dark, dense objects exist, but there are far too few of them to account for the missing mass. And an independent line of reasoning closed the door completely. The theory describing how the lightest elements formed in the first minutes after the Big Bang sets a firm limit on how much ordinary matter the universe can contain, and that limit is close to the same 5% we keep arriving at. There is simply not enough ordinary matter to be the dark matter, no matter how well it is hidden. Whatever the ghost is, it is not made of protons and neutrons. So theorists turn to particles that do not yet appear in the Standard Model, at all particles that might exist just beyond the reach of our accelerators. Over decades of work, 2 leading candidates emerged. The first is the WIMP, the weakly interacting massive particle. It was born out of a mathematical framework called supersymmetry, developed in the 1970s and 80s to smooth over certain inconsistencies in the Standard Model. Supersymmetry proposed that every known particle has a heavier, undiscovered partner, and when physicists ran the mathematics, the equations naturally produced a new particle heavy, perhaps 100 times the mass of a proton, perfectly stable, and blind to electromagnetism. The only forces it could feel were gravity and the weak nuclear force. the force responsible for certain kinds of radioactive decay, which acts only across distances smaller than an atomic nucleus. In other words, a weakly interacting massive particle. But the most compelling thing about the WIMP was not that it matched the description. It was a coincidence that physicists came to call the WIMP miracle. If you take the equations of thermodynamics and model the searing heat of the early universe, you can calculate how such particles would have behaved. In the first fractions of a second, they would have been constantly colliding and annihilating into pure energy, while high-energy radiation collided to spawn new ones, a chaotic equilibrium of creation and destruction. But the universe was expanding, and as it expanded, it thinned. Eventually, the particles were spread too far apart to find each other and annihilate. The creation and destruction stopped. The population froze at whatever number happened to survive, and when physicists calculated how many WIMPs should have survived that freeze-out, using the mass and interaction strength that supersymmetry predicted, the number they got accounted for very nearly the exact amount of dark matter that astronomers were measuring in the sky. Two completely separate lines of reasoning, particle theorists at a chalkboard and astronomers at a telescope, had arrived at the same figure from opposite directions. It felt like the universe was handing over the answer, wrapped neatly in the laws of thermodynamics. For an entire generation of physicists, the WIMP miracle was persuasive enough that it seemed it almost had to be true. The second candidate is very different. It is called the axion. Like the WIMP, it was not invented to explain dark matter. It was proposed in 1977 to fix an obscure flaw in the behavior of the strong nuclear force. But if the axion exists, it is the opposite of the heavy, bullet-like WIMP. It would be almost inconceivably light, perhaps 1 trillion times lighter than a single electron. It would take a staggering number of them to supply the gravitational weight of the cosmic web. And because it is so light, its quantum wavelength would be enormous, large enough to be macroscopic. It would not behave like a swarm of tiny individual particles drifting through your room. It would behave like a single, coherent, invisible fluid. If dark matter is made of axions, then the halo around the Milky Way is a vast, cold, invisible ocean, slowly sloshing, and the Earth is simply drifting through its silent waves. The weakly interacting particle and the axion are the two most studied candidates, but they are far from the only ones, and it is worth appreciating how wide the field of possibilities really is. There is a proposed particle called the sterile neutrino, a heavier, more reclusive cousin of the ordinary neutrino, one that would ignore even the weak nuclear force and interact through gravity almost alone. For a brief period, there was excitement about it, when astronomers studying the X-rays from distant galaxy clusters reported a faint, unexplained spectral line at a very specific energy, the kind of signal a decaying sterile neutrino might produce. Other teams looked and could not agree on whether the line was real or an artifact of the instruments, and the matter remains unresolved to this day, a small, tantalizing question mark in the X-ray data. Then there is a candidate that requires no new particle at all. Some physicists have proposed that the dark matter might be made of black holes formed not from collapsing stars, but directly in the first instance after the Big Bang, when the universe was dense enough that regions of it could collapse on their own. These primordial black holes would be dark, they would be stable, and they would supply gravity without any exotic new physics. The idea faded for a time, then surged back to life when gravitational wave detectors began observing collisions between black holes of unexpected masses, and some wondered whether these could be the primordial population. Careful searches have since ruled out primordial black holes as the whole of the dark matter across most of the mass ranges they could occupy, but a few narrow windows remain open, and the idea has not entirely gone away. Step back, and the situation is almost comic in its breadth. The candidates that physicists take seriously span an enormous range of possible masses, from the fuzziest, lightest proposals, particles so light and so spread out that a single one would be smeared across an entire dwarf galaxy, all the way up to black holes many times heavier than the Sun. That is a span of something like 90 powers of 10 between the lightest and heaviest serious candidates. We have measured the total weight of the dark matter to within a few percent. We have mapped where it sits across billions of light years, and we cannot yet say whether a single one of its particles is lighter than an electron or heavier than a star. That is the strange shape of our ignorance. It is not vague, It is precisely bounded on the large scale and completely open on the small. Armed with the elegant mathematics of the WIMP and the axion, the physics community shifted from theory to action. They knew what they were hunting, and they knew the rules of engagement. Because these particles might, very rarely, interact through the weak force or convert into light under extreme conditions, it was in principle possible to catch one. We simply had to build a trap, patient enough and quiet enough to wait for the ghost to touch it. To find out how far we are willing to go for that, and to what extremes of silence and isolation we are willing to subject ourselves, you have to travel to the Black Hills of South Dakota. In the town of Lead, there is an industrial complex built into the side of a mountain, the surface entrance to the Sanford Underground Research Facility. For more than a century, this was the Homestake Mine, the deepest and largest gold mine in North America. Generations of miners drilled and blasted their way through the rock, carving a vast network of shafts and tunnels plunging deep into the crust of the earth. Today, the gold is gone, and the depth itself has become one of the most valuable resources in modern physics. The mine has history in this exact kind of work, and it is worth knowing, because the hunt for dark matter is the direct descendant of an older hunt carried out in these same tunnels. For most of a century, men descended into this rock to pull out gold, following the veins deeper and deeper until the shafts reached well over a mile beneath the surface, into hot, cramped darkness where the walls had to be cooled to make the work survivable. When the gold finally ran out and the mine closed, that enormous depth, which had cost so much to dig, was suddenly available for something else. Long before the dark matter detectors arrived, a physicist named Raymond Davis carried out one of the most important experiments of the 20th century deep inside this mine. He was trying to catch neutrinos, the ghostly, nearly massless particles streaming out of the core of the sun by the trillion. Neutrinos are not dark matter, but they share the crucial, maddening property of almost never interacting with anything. Trillions of them pass through your body every second, day and night, straight through the entire Earth, and you never feel a single one. Davis wanted to prove they were there, so he filled an enormous tank with hundreds of thousands of litres of ordinary dry cleaning fluid, because its atoms held a kind of chlorine that would, very rarely, absorb a neutrino and transform into a countable atom of argon. He placed the tank deep in the mine, under the shielding mile of rock, and he waited for years, counting individual atoms, a handful of them at a time, produced by the passage of particles from the heart of the sun. His experiment worked, and it delivered a shock. He caught the solar neutrinos, proving they existed, and that we were seeing directly into the nuclear furnace of the sun for the first time. But he caught only about a third as many as the theory of how the sun burns had predicted. 2/3 of the expected neutrinos were simply missing. This became known as the solar neutrino problem, and it haunted physics for decades. The resolution, confirmed much later, was extraordinary. The neutrinos were not missing at all. On their 8-minute journey from the sun, they were transforming, shifting from one type into another that Davis's tank could not detect. The particles were changing their identity in flight. It meant the neutrino, long assumed to be massless, had to carry a tiny sliver of mass after all. Davis lived to receive the Nobel Prize for the work he began in the dark of this mine. That is the lineage of the dark matter detectors now sitting in the same rock. Physicists learned, in these tunnels, how to build an instrument patient and quiet enough to catch a particle that barely interacts with matter at all, how to count single atoms against the silence, how to trust a signal so faint it arrives only a few times a year. Everything they learned hunting the neutrino, they carried forward into the hunt for the ghost. To understand why physicists need a gold mine, you have to understand the noise of the surface world. The surface of the Earth is, from a detector's point of view, deafening. We are constantly bombarded by cosmic rays, high-energy particles thrown out by exploding stars, active black holes, and the sun. When these strike the upper atmosphere, they shatter, cascading into showers of secondary particles. One of those secondary particles is the muon. Billions of muons rain down on the surface every second. They pass harmlessly through your house and your body and into the ground. But for a dark matter detector, they are a catastrophe. Build a sensitive detector on the surface, and it is instantly blinded by the relentless hail of muons, trying to hear the microscopic, incredibly rare whisper of a dark matter particle in that environment is like trying to hear a single snowflake land while standing in a hurricane. You cannot switch the cosmic rays off, and you cannot build a shield thick enough to stop them by ordinary means. The only way to find the silence is to put an enormous amount of solid matter between your detector and the sky. You have to use the Earth itself as the shield. At the Sanford facility, physicists board a heavy industrial cage and begin a slow descent down the shaft. The sunlight vanishes. The air pressure climbs, popping the ears. The surrounding rock grows warmer the deeper they go, heated from below by the planet's interior. They descend roughly 1,500 meters. Nearly a full mile of solid rock now hangs directly above their heads. At this depth, the cosmic noise is almost entirely gone. That mile of dense rock absorbs the muons, filtering out the background clatter of the universe, and what remains is one of the quietest physical environments on the planet. Here, in a cavern carved from ancient stone, physicists built one of the most sensitive dark matter detectors ever made. Its heart is a vat holding 7 tons of ultra-pure liquid xenon. Xenon is a noble gas, but cooled to around -100 degrees Celsius, it condenses into a dense, heavy, perfectly transparent liquid. It was chosen for a specific reason. Its atomic nucleus is large and heavy, which makes it a broad target. The strategy is entirely passive. The physicists hold the liquid xenon in absolute darkness, and they wait. They wait for a single dark matter particle to drift into the tank and, by pure chance, strike a xenon nucleus almost dead center. The word chance is doing an enormous amount of work in that sentence. Remember that dark matter almost never touches ordinary matter that is its defining trait. An individual dark matter particle could pass through a slab of solid lead, stretching from here to the far side of the galaxy and stand a good chance of never striking anything at all. So even though a vast flux of these particles is pouring through the tank every second, the number expected to actually collide with a nucleus, hard enough to register, might be only a handful in an entire year. This is the reason the detectors must be so large and so pure and so patient. You cannot make the collision more likely, because the particle obeys its own indifferent physics. You can only give it more nuclei to possibly hit, and then remove every other source of noise so completely that when one of those exceedingly rare collisions finally happens, you will not mistake it for anything else. The whole apparatus, the tons of xenon, the mile of rock, the nested shields, the years of waiting, exists to catch a few faint taps a year from a substance that would rather not be caught at all. When such a strike happens, the nucleus recoils, and as it bounces through the surrounding liquid, it jostles the other atoms and produces a microscopic, instantaneous flash of ultraviolet light. To catch that flash, the top and bottom of the tank are lined with nearly 500 photomultiplier tubes, so sensitive they can register the arrival of a single photon. If the ghost touches the xenon, the tubes will see it. But building this trap demanded a level of caution that borders on the obsessive. The mile of rock blocks the cosmic rays, but the rock itself creates a new problem. The cavern walls contain microscopic traces of naturally radioactive elements, uranium and thorium, and as those decay they emit radiation. A stray gamma ray from the wall, striking the xenon, would produce a flash that looks exactly like a dark matter collision. To defend against this, the engineers built a nested series of shields, one inside another. The liquid xenon sits inside a vessel of the purest titanium on Earth. That vessel hangs inside a larger tank filled with tens of thousands of liters of a liquid designed to catch stray radiation. And that assembly hangs inside a still larger tank holding hundreds of thousands of liters of ultra-pure water, a final moat absorbing the natural radioactivity of the surrounding rock before it can ever reach the detector. The greatest threat, though, was not the rock. It was the physicists themselves. A single speck of ordinary household dust carries enough trace radioactivity to spoil the measurement. A flake of skin, a stray hair, a fingerprint left on the inside of the titanium vessel would emit enough false signals to overwhelm the tubes. And the assembly happened to take place at the height of the global pandemic, in 2020, a time already defined by extreme human isolation. The surface world had shut down, cities were quiet, borders were closed, and a mile beneath South Dakota, a small team pushed that isolation to its physical limit. They worked inside a custom cleanroom erected within the cavern. Before entering, they passed through decontamination showers and dressed in full sterile suits. double gloves, masks, hoods, only their eyes exposed. They moved slowly and breathed filtered air, taking care that the outside world could not contaminate the trap. They spent months in that underground cleanroom, washing every bolt and wire and sheet of titanium in acid to strip away any radioactive residue left over from manufacturing, assembling the fragile wire grids and the sensitive tubes by hand in the muffled quiet, surrounded by a mile of crushing rock. They built the most sensitive listening device in the history of human civilization. They sealed the vessel, filled it with xenon, and switched the sensors on. The engineering was flawless. The background noise of the universe had been filtered out. The xenon sat cold and still in the dark, waiting for the invisible scaffolding of the cosmos to make a sound. The scientists collected data for months and analyzed millions of microscopic signals, filtering out every known source of stray radiation, searching for the specific energy signature of a collision. The data came back clean. The xenon did not flash. The tube saw nothing. The heavy particles predicted by the elegant mathematics of supersymmetry did not strike the atoms in the tank. The silence was not a failure of the machine. The machine listened exactly as it was designed to. The silence is a statement from the universe. It is a narrowing of the possibilities. It tells the physicists that if the ghost exists as a particle at all, it is even lighter, even more ghostly, even more detached from the ordinary world than our most extreme mathematics predicted. And this is not one detector's story. Similar experiments running deep beneath a mountain in central Italy have returned the same silence, and each new generation of detector, built larger and cleaner and more sensitive than the last, has pushed the boundaries of where the WIMP could be hiding without ever finding it. Meanwhile, entirely different experiments hunt for the axion instead, using powerful magnetic cavities designed to coax an axion into converting into a single detectable photon of microwave light. They too have searched patiently, and they too are still waiting. The deep xenon detector represents only one of three great strategies humanity has thrown at this problem, and it is worth understanding all three, because the silence is coming from every direction at once. The first strategy is the one we have just described: direct detection, waiting in a shielded vault for a dark matter particle to strike an atom. The second is to reverse the logic entirely and try to create dark matter rather than catch it. This is the work of the great particle accelerators, machines that smash ordinary particles together at nearly the speed of light, briefly concentrating enough energy in a tiny space to bring heavy new particles into existence. The largest of these accelerators has been searching for years for a telltale sign, a collision in which some energy simply vanishes, carried off by a particle that passed through the detectors without leaving a trace, exactly as dark matter should. It has produced a great deal of superb physics. It has not produced dark matter. The particles predicted by supersymmetry, which should have appeared at the energies the machine can reach, have not appeared. The third strategy is to look outward instead of inward, to watch the dark matter halos in the sky, and hope to catch the particles destroying one another. If the dark matter is its own antiparticle, as many models suggest, then in the densest regions of a halo, two particles should occasionally meet and annihilate, converting their mass into a flash of ordinary radiation, a burst of gamma rays. Space telescopes designed to map the gamma ray sky have stared at the places where dark matter should be thickest, above all the crowded center of our own galaxy, searching for an excess glow that ordinary sources cannot explain. And here, unlike in the underground vaults, they did find something. There is a genuine excess of gamma rays coming from the center of the Milky Way, more than the known stars and gas seem able to account for. For a time it looked like it might be the long-awaited signal, but the galactic center is a crowded, complicated place, and the excess can also be explained by a large population of rapidly spinning dead stars, pulsars, too faint to count individually. The question has not been settled. It sits, like the X-ray line, like the train wreck cluster, in the file of things that are suggestive and unresolved. There is one anomaly that refuses to go quietly, and it deserves an honest mention. Deep under that same Italian mountain, a long-running experiment using crystals of sodium iodide has reported, for more than 2 decades, a curious signal that rises and falls with the seasons. The reasoning behind it is elegant. As the Earth orbits the Sun, our planet's motion through the galaxy's dark matter halo speeds up and slows down over the course of a year, so the rate at which dark matter particles strike a detector should rise and fall on an annual cycle. This experiment sees exactly such a cycle, with striking statistical strength, peaking and dipping at just the times the theory predicts. By its own numbers, it is a detection, and yet almost no one in the field is convinced, for a simple and damning reason. Every other experiment, built to check the claim, has looked for the same signal and found nothing. When one instrument sees a clear signal that no other instrument can reproduce, the scientific instinct is not to celebrate, but to suspect that something about that one instrument, its materials, its environment, some seasonal effect no one has identified, is producing a false pattern. The claim has neither been confirmed nor cleanly killed. It remains one of the strangest standoffs in modern physics, a signal that behaves exactly as dark matter should, that almost no one believes is dark matter. It is worth being clear about why so much effort, so many careers, so many years spent a mile underground are poured into this hunt. If any one of these experiments ever catches a dark matter particle cleanly and convincingly, if the xenon flashes in a way that cannot be explained by any known source, and another detector confirms it, it would be the first genuinely new particle discovered outside the standard model in the entire history of physics. It would be direct, laboratory contact with the substance that makes up most of the matter in the universe, a substance we have only ever felt through its gravity across millions of light years. It would open a door onto whatever larger theory lies beyond our current picture, the deeper physics that the standard model is only a piece of. This is why the silence is not treated as failure but as data, and why each null result is published and built upon, rather than buried. Every experiment that comes up empty narrows the space where the answer can be hiding, and tells the next generation of physicists where not to look. The search continues not because anyone is certain it will succeed, but because the prize, if it comes, is a piece of the universe no one has ever held. There is a specific, quiet difficulty in this era of physics. It is the recognition that elegance in mathematics does not obligate the universe to comply. A theory can be beautiful. It can solve several problems at once. It can offer a coincidence as clean as the WIMP miracle, and it can still be entirely wrong. The universe does not care whether our equations are beautiful, which leaves us in a strange and vulnerable position. The telescopes insist the mass is there, the rotation curves demand it, the lenses map its shape. The cosmic web defines our place in the void. The large-scale universe testifies, with undeniable gravitational weight, that the ghost is real, and yet the small-scale universe stays silent. The particles refuse to announce themselves in our finest instruments. We know they are passing through us right now, because the mathematics of gravity leaves no other option, but we cannot make them speak. And so we are forced to rely on a different kind of evidence, not a signal we catch, but a receipt the universe printed long ago, at the very beginning, in a flash of light that still surrounds us. To read it, we have to leave the deep earth behind and look all the way back to the first moments of the cosmos. For the first 380,000 years after the Big Bang, the universe was a place where light could not travel. It was expanding, but it was still small, dense, and blindingly hot, a roiling ocean of subatomic particles. Protons and electrons and dark matter crushed together in a state of superheated plasma. In that plasma, light was trapped. A photon cannot move easily through a crowd of free electrons. The instant it tried to cross the early universe, it would slam into a high-energy electron, bounce off, travel a fraction of a millimeter, and strike another. The universe was full of light, and yet completely opaque, a blinding, glowing fog. Standing inside it, you would not have been able to see your own hand. But the universe was expanding, and as it expanded, it cooled. 380,000 years in, the temperature fell to roughly 3,000 degrees Celsius, and something changed. At that temperature, the free electrons finally lost enough energy that they could no longer resist the pull of the protons. In an event called recombination, the electrons settled into orbit around the protons, and the first neutral atoms of hydrogen and helium formed. All at once, the crowd of free electrons was gone. The fog cleared. For the first time, the photons were free to move without colliding. They broke out of the plasma and streamed across the newly transparent universe in every direction, in straight lines, and they have been travelling ever since. That great, simultaneous release of light is the oldest light in existence, and it has been on its way to us for 13.8 billion years. There is a way of picturing this that makes it more concrete. When you look up at the cosmic microwave background, you are not looking at a scattered collection of objects. You are looking at a wall, because the light was released everywhere at once, at a single moment in cosmic history, and because light travels at a fixed speed, the oldest light reaching us today comes from a spherical shell at a fixed distance all around us. The exact distance light could travel in the 13.8 billion years since the fog lifted. Astronomers call this shell the surface of last scattering. It is the boundary of what we can ever see. No telescope, however powerful, can look past it, because before that moment, the universe was opaque, and there is simply no light from before it to catch. When you point an instrument at the microwave background, in any direction, you are seeing the wall of the early universe as it was 380,000 years after the beginning, the furthest back that light itself allows us to look. Everything we know about the composition of the cosmos, including the exact amount of dark matter, is read off the faint temperature ripples printed on that wall. And the wall is not somewhere out at the edge of things. It surrounds us on all sides, and it is drifting steadily further away as the universe ages and the light from ever more distant regions finally arrives. We sit at the center of our own observable sphere, wrapped in the light of the beginning, reading the receipt printed into it. As it traveled, space itself kept expanding, and the light stretched with it. The short, high-energy waves of the original flash were pulled out longer and longer, shifting down out of the visible range, through the infrared, and finally settling into the microwave part of the spectrum. Today, this ancient light washes over the Earth from every direction in the sky as a faint, constant hum of microwave radiation. We call it the cosmic microwave background. Its discovery is one of the great accidents of modern science. In 1965, two radio astronomers named Arno Penzias and Robert Wilson were working at the Bell Telephone Laboratories in New Jersey, using a large, sensitive horn antenna originally built to catch radio signals bounced off early communications satellites. They wanted to map faint radio emission from the Milky Way, and before they could do that, they had to eliminate every source of background noise. They pointed the antenna at an empty patch of sky, expecting silence, and instead, they heard a low, persistent hum. It came from everywhere. It did not matter whether they aimed at the center of the galaxy or the darkest void, whether it was day or night, summer or winter. The hum was always there, and always the same. They assumed the equipment was faulty. They checked the wiring. They cooled the receiver. At one point, they discovered that a pair of pigeons had been roosting inside the throat of the antenna, and they climbed in and scrubbed out the accumulated droppings, suspecting the mess might be generating a false heat signal. They evicted the pigeons, cleaned the metal, and switched the antenna back on. The hum was still there. Penzias and Wilson did not know what they had found until they contacted a group of theoretical physicists at nearby Princeton who had been calculating what the leftover flash of the Big Bang should look like today and had predicted a faint microwave glow at a temperature just a few degrees above absolute zero. The two radio astronomers had accidentally tuned their antenna to the light of the early universe. In the decades that followed, humanity launched a series of satellites to study this ancient light, with ever greater care first, an observatory called the Cosmic Background Explorer, then the Wilkinson Microwave Anisotropy Probe, and later the Planck Observatory. The first of these did two things that reshaped cosmology. It measured the color of the ancient light with such precision that it matched the theoretical prediction for the afterglow of a hot, dense beginning, almost perfectly. One of the most exact agreements between theory and observation ever recorded, and about as close to a direct confirmation of the Big Bang as physics has ever come. And it produced the first crude map of the tiny temperature variations across the sky, the first glimpse of the faint patchiness that everything else would be built upon. The two physicists who led that work were later awarded the Nobel Prize. The instruments that followed took that faint patchiness and sharpened it, from a blur into a detailed portrait. These instruments mapped the temperature of the oldest light across the whole sky with extraordinary precision. When you look at the maps they produced, the cosmic microwave background appears as a mottled oval covering the entire sky, speckled with faint patches of slightly different color. The colors represent temperature. The light is astonishingly cold, averaging just under 3 degrees above absolute zero and remarkably uniform. But it is not perfectly smooth. Some regions are 100,000th of a degree warmer than average, and some 100,000th of a degree cooler. Those microscopic variations are not random noise, they are fossilized sound. They are the frozen imprint of pressure waves that rippled through the plasma of the early universe. In that first chaotic era, ordinary matter and radiation were locked in a struggle. Gravity, driven by the heavy concentrations of dark matter, pulled the ordinary hydrogen plasma inward, trying to compress it into dense knots. But as the plasma compressed, it heated, and the trapped photons pushed back outward with intense pressure, blowing it apart again. The plasma fell in, bounced out, fell in, bounced out, and this rhythmic compression set up enormous waves traveling through the fog, a slow cosmic ringing. When the universe suddenly cleared, those waves were frozen in place. The regions caught in compression became the slightly warmer spots on the map. The regions caught mid-expansion became the slightly cooler spots. And here is where the receipt is printed. By measuring the exact size, spacing, and intensity of these warm and cool spots, cosmologists can reconstruct precisely how much gravity was pulling inward and how much radiation was pushing outward. At the moment the fog lifted, dark matter has mass, so it added to the gravity, pulling the plasma in. But dark matter ignores light, so it felt none of the radiation pressure pushing out. Ordinary matter felt both. Because the two kinds of matter behaved differently inside the plasma, they left two distinct signatures in the frozen waves. The pattern of the spots, their heights, their spacing, the relative strength of one ripple against the next, is an exact inventory of what the universe was made of at the dawn of time. There is a specific and beautiful piece of this that deserves to be spelled out, because it is the point where dark matter signs its name in the light. When cosmologists take the map and measure how much of the temperature variation occurs at each scale, how much at large patches, how much at medium patches, how much at small, the answer is not a smooth curve. It rises and falls in a distinct series of peaks, like the harmonics of a struck bell. The first and largest peak tells us about the overall geometry of the universe, and it says, unambiguously, that space is flat. The second peak, and the way it sits lower than the first, measures the amount of ordinary matter. And the third peak carries the fingerprint of the dark matter. Because dark matter added gravity, but felt no radiation pressure, it changed the balance of the ringing in a particular way, boosting certain harmonics relative to others. The precise height of that third peak, measured across the whole sky, is one of the cleanest measurements of the dark matter density that exists. It does not depend on any galaxy, any cluster, any lens. It comes straight from the sound of the infant universe. And the number it gives agrees, to within a few percent, with the number derived from the motions of galaxies and the bending of light. 3 completely different methods, probing 3 completely different epochs of cosmic history, converge on the same value. The frozen sound left one more fingerprint, and it is one we can still find in the sky today. Those pressure waves rippling through the early plasma did not travel forever. They were traveling outward from every dense spot when the universe suddenly cleared and the waves froze in their tracks, leaving each original concentration of matter surrounded by a faint shell at a fixed distance, the distance the sound had managed to travel before it stopped. That distance became a kind of ruler, printed into the universe at the beginning. And because galaxies later formed preferentially both at the original spots and along those frozen shells, there is, even now, a very slight preference for pairs of galaxies to be separated by that one particular distance, a whisper of extra structure at a scale of roughly 500 million light-years. When astronomers surveyed millions of galaxies and measured the separations between them, they found exactly that faint preferred distance, sitting in the data like a fossil. The ruler laid down in the first light of the universe is still legible in the arrangement of galaxies 13 billion years later, and it too depends on the presence of dark matter to come out right. The numbers are written into the light. The measurements show that ordinary matter, the protons and neutrons and electrons, the raw material for every star and planet and living thing that will ever exist, makes up about 4.9% of the total content of the universe. Dark matter makes up about 26.8%. The remaining 68.3% is dark energy, the mysterious force accelerating the expansion of space, which is a story for another night. It is worth pausing just long enough to keep these two dark things apart, because they are constantly confused, and they are almost opposites. Dark matter and dark energy share only a name, and the fact that we cannot see either one. In every other respect, they behave in contrary ways. Dark matter is a substance. It has mass, it clumps, it gathers under gravity, it builds structure. Its entire role in this story is to pull things together, to dig the wells that galaxies fall into. Dark energy is not a substance at all, at least not in any familiar sense. It does not clump, it does not gather, it is spread perfectly evenly through all of space, and instead of pulling things together, it pushes them apart. It is the reason the expansion of the universe, which everyone once assumed must be slowing down under the collective gravity of all its matter, was discovered near the end of the 20th century to be speeding up instead. Something is overpowering the inward pull of all the matter in the cosmos, dark and ordinary alike, and driving everything apart at an accelerating rate. That something is dark energy, and it is the largest single component of the universe, and we understand it even less than we understand dark matter. Two great darknesses then, one that assembles and one that disperses. Together they make up about 95% of everything, and the bright, tangible world we evolved to see is the sliver left over. But strip away the dark energy and look only at the physical matter, the material that clumps, that builds gravitational wells, that assembles the scaffolding of reality, and the ratio is stark. Roughly 15% ordinary matter, roughly 85% invisible. This is not an inference from one strange galaxy. It is not a local error from one telescope watching one cluster collide. It is the fundamental composition of the universe we live in, read directly from a flash of light that spans the entire observable cosmos, and confirmed by three separate independent lines of evidence that all agree the motion of galaxies, the bending of distant light, and the frozen sound of the beginning. The deep detector in South Dakota may sit in silence for another century. The elegant equations of the WIMP miracle may eventually be discarded. We may have to invent entirely new physics to understand how a substance can carry such enormous gravitational weight while refusing to touch a single atom of the ordinary world. But the mystery of what it is does not weaken the certainty of where it is. We do not need the ghost to speak in the mine, because we can already see the shadow it cast on the first light of creation. Return, now, to the room where you are lying. Listen to the quiet around you. The walls feel solid. The bed beneath you feels permanent. The air moving through your lungs feels like the ordinary default state of things. But you know the context of that feeling now. You exist because a halo of dark matter cooled out of the chaos after the Big Bang and dug a gravitational well deep enough to catch the drifting hydrogen that would one day ignite into the sun. You are resting on a small speck of ordinary matter, sliding along an immense invisible filament of the cosmic web, falling slowly toward the center of a supercluster whose name means immense heaven. And in this exact moment, the silent rain is still passing through the dark. Billions of invisible particles are moving through the roof, through the blankets, through your body, every second. They do not slow, they do not touch your atoms, they leave no trace. We can map this invisible ocean across millions of light years. We can weigh it by reading the frozen sound of the oldest light in the universe. We owe the entire existence of the visible world to its gravity, and after a full century of searching, we still cannot say what it is. That indifference is not cruelty. It is not a failure of science, and it is not a reason to be afraid of the dark. It is simply the shape of the universe. We happen to live in a universe far larger, stranger, and heavier than the thin sliver of light we were built to see.